Last dance on the Titanic, guys. Okay, so this is a more complicated reaction, and it's good to see because this will show you, again, I never want to dissuade you out of a problem solving method, and I believe it's good to have multiple tools in your toolbox. I did not do the rice tables for Stoic until last year. You'll have to do rice tables for another concept if you take AP Chem with me. They're great for equilibrium. It's a little bit harder when you start getting all of these numbers for coefficients and you don't have a 1 in there to really help kind of center yourself. So let me show you. So this is butane reacting with oxygen to give you carbon dioxide and water. Okay. And again, I'm trying to pick things so you don't have to reinvent your molecular masses. So 130 grams of butane and 400 grams of oxygen. So first step is simple. Get your moles. So 130 divided by 58 is 2.24 moles of butane. And 400 divided by 32 is 12.5 moles. Well, now you've got to do a comparison to get your limiting reagent. And that's not too hard. Well, it's a 13-to-2 relationship. You could just say it's a 1 to 6.5 to make it easy, but let's use our equation. So theoretically, if I wanted to see if this comes out perfect, take my 2.24, if I multiply it by 13 halves, I would need 14.56 moles of oxygen for it to come out perfect. So if I've got more oxygen than 14.56, my butane's my limiting reagent. And if I've got less oxygen than 14.56, the oxygen's my limiting reagent. I've got 12.5 moles of my oxygen. Oxygen's my limiting reagent. Okay. So now we've got to figure out for a second, oh crud, I don't have 1s and 2s in here. I need to figure out what are the moles that go into this. Well, okay, well how much butane is actually gonna disappear? Well, I've got to use my relationship based off of how much oxygen I have. Well, 12.5 times 2 divided by 13, because I've got to use my molar relationship now. Well, that's 1.92 moles. Oh, well, that makes sense. I'm going to have some butane that's left over. Well, now for my carbon dioxide, what's going to go into the rice table? Well, it's going to be 12.5 times 8 divided by 13. Oh, crud, that's 7.69 that goes in there. And then the same thing for water, the 12.5 times 10 divided by 13. Well, that's 9.62. Guys, the point is, if you're doing this much math just to set up your rice table, at this point, you're one step away from having done the math step. So you might as well do the math at that point. Now, if it's like a 2 to 4 to 6 to 5, where there's just one number that's off and there's kind of like an even number relationship in there that makes it a little bit simpler, maybe you can convince me. This is really wonky. I'll show you the rice table anyway, because it's still there. And let's have the numbers come out. And then I'll show you the math method. So, rice table. Okay. So here it is. It's just like what I showed in order to set it up. Here's your 12.5. Here's your limiting reagent. You don't have any products having been made. And here's your 2.24 moles of butane to start. When the reaction runs, your oxygen is going to disappear. You're going to lose 1.92 moles of this. You're going to make 7.69 and 9.62 moles of your water. Okay, so when you're done, you're going to have a little bit of butane left. All of your oxygen's gone. You've got 7.69 moles of carbon dioxide and 9.62 moles of water. And by the way, if you look at this, you can almost see it because you've got 12.5 moles here and 13 there. And so 7.69 is almost 8, 9.62 is almost 10. So you can almost, with this one problem, it just so happened the numbers worked out that way, that you can kind of see that the ratios are working, but you can't count on that happening. So yeah, the rice table works, but you've got to be really good with your math. And you could have waited until you set up your rice table to do it. But if you're not careful, you're going to mess something up, and then you're going to get completely the wrong answer. But let's set up our answer. See how much carbon dioxide and water we made. So 7.69 moles times 44 grams, a little bit over 338 grams of carbon dioxide. Yeah, that's just your molecular masses. I didn't write those at the top of the equation. Water, here's your moles, 9.62 from the end line of your rice table. Water has a molecular mass of 18 grams, so 9.62 times 18, so a little bit over 173 grams of water. Okay, so let me convince you now, when I flip this over, you've identified your limiting reagent when you said, okay, I made the comparison, I've seen that I'm going to run out of oxygen first. Let me just do the math so I don't have to try to do all that crazy comparison for my moles, in my rice table. Let me just do the math. So last one. So you take your starting amount of oxygen, you convert into moles, divide by your molecular weight of oxygen, which is 32 grams. Well, now I'm in moles of oxygen. Oh, you saw where I pulled that little trick from to set up the rice table. 13 moles of oxygen converts into 8 moles of carbon dioxide. Oh, I am just one step away now. 1 mole of carbon dioxide is 44 grams. And you saw how similar your answers were. Again, you're not having to truncate your answer. You're not having to chop off on decimals for your rice table. But it's the same work with your rice tables. You're just choosing to do all of your math together here. For water, same thing again. 400 grams of oxygen, convert into moles. I'm out of grams, I'm into moles of oxygen, divide by the molecular weight. Use my balanced chemical equation, say, oh, 13 moles of oxygen gets converted into 10 moles of water. I'm in moles of water now. Just like I had to do all that math to set up the rice table for this particular equation because it's so much more complicated. Now, use my molecular mass to get back into grams of water, and when I punch all that in, I get 173 grams of water. Very similar to the other answer I got. So, limiting reagent problems. Which of my reactants is going to determine and put a cap on how much of my products that I could make? You can do it with your rice tables. You can do it with your math method. Either method will completely work, and as long as your chemical equations don't start getting super complicated, there's really no advantage to one way over the other. Just make sure you know what the chemical equation means. So if you've got a 1-to-1 relationship versus a 1-to-2 relationship, you know that if it's 1-2, sometimes you need 2 molecules to disappear, and you're going to need twice as many of them. You're going to need a lot of practice. Don't be afraid. Don't be afraid to make mistakes. It's going to happen. You see how deliberately I move and I talk here, and I've been doing this for a while. Get your practice in. Let's talk about this, and don't be afraid to show your work. It'll be a lot easier to catch your mistake if you do. All right? See you next time. Good work. Stay healthy. Stay safe. Bye, guys.